Coming up next on the IP Talk stage, Patrick Soheili from eSilicon presenting Chip PPA Optimization with custom IP.
There are players in the marketplace, and if we can't find it there yet, because they're all built compilers, we will try to optimize further by using our own compiler technology, memory compiler technology, and optimizing the instances that we see most commonly in those designs. This is a very significant advantage that is then passed on to the device itself. I'll talk more about that in a second. So a little bit about eSilicon just to kind of reintroduce the concept, but we have some close to 75 or 100 customers worldwide. Anything from a very small device that is sold in the open market for tens of cents, all the way up to network processors, very complex devices built by large companies that you see names up there for hundreds of dollars and dissipating tens of watts, and anything in between. So we do lots of different chips for lots of different folks. We use a lot of the industry standard products, technologies, offerings, services, and foundry services, as well as EDA tools and IPs. And there are three divisions within eSilicon that leverage those. The ASIC division, which is our largest and kind of the foundation of the business. It takes customers' net lists and takes it all the way through production, so it's a turnkey service. The SMS business unit that started about a couple of years ago will try to look for fabless companies that have operations departments that can be synergized with ours, because we do the exact same thing as most of those companies do. And by synergizing those, there's usually a lot of waste that could be purged out of the system, and we could produce a better chip together. And then the IP business unit, which started about 2 years ago by us acquiring a company called SDS for Silicon Design Solutions in May of 2010. So I wanted to give you some examples of why optimization, or how optimization can help. First, why, and then how. So I'm going to give you a real live example. This is a device that we're actually making, and we're under contract for making. It goes into a digital TV. It's the main processor. Some 40+% of the area is consumed by different memory types. Some 2,577 memory instances, with 525 of those being unique, are used in those designs. And by taking and optimizing 21 of those instances, of those 525 instances, we actually were able to save 5 millimeters square of the device, which is roughly 10% of the device. So this is a significant savings when you're talking about either cost reduction or power reduction or anything related to that. Another example might be where an application requires more speed. Same sort of a phenomena applies there. You look at the number of instances that are being used, what's on a critical path. You take memories coming out of compilers, and if you use them as is, you have a lot of overhead, you have a lot of burden that's associated with that, because they're designed in a compiler kind of a methodology. You take those, you strip those down of the overhead that you see for that specific critical path, and you can then design yourself something that's a lot more efficient and a lot more productive, especially in the case of building fast cache instances for high-speed processing and subsystems in a lot of the multimedia and mobile applications, as we see. This is an example of a product that we taped out August of last year with two companies. We used 3 cores in a cluster from MIPS, a 1074 core. We taped out a test chip in 28 nanometer SLP process in Global Foundries, and we were able to, just by customizing the fast cache instances in the level 1 cache, increase the performance by a good 20% on worst case corners. That increased performance could amount to somewhere between 50 and 75% if you're looking at typical conditions, and a lot of the systems that we might be talking about from a consumer point of view may not require the typical conditions. But at the worst case conditions, 1 gigahertz, And this was designed to kind of prove the point that by optimizing and when you need to, using optimized instances and not the off-the-shelf compilers, you can actually gain a significant amount of advantages. So with the convergence of computing power required, the convergence in computers themselves, by requiring a lot of this mobility and content creation that we're facing. Power is also very important. Battery life is very important. Energy produce is very important. And in 28 nanometer technologies, for the most part, this complication by adding more and more transistors and more devices onto your chip just becomes as complex, even more complex. And the best combination of operating voltage and threshold implants can actually bring a lot of advantages. And the case that I want to bring to you is when we're able to kind of dislocate the memory array from the actual peripheral, drive the peripheral with, for example, a different VT than the standard VT that we're using for the memory array, and that way, by overdriving and then using some of the other tricks that we have in our compiler technology, we can actually bring down the overall power dissipation of the device by a good 20 to sometimes 30%. So a big advantage again in static timing, static power or standby power of fine geometries ASICs. This example is also another one that we're working on currently. It's a very large networking chip, some 50 megabyte of memory on this device. So it's a significant chip. We've looked at this, and again, we've been able to find traces of duplicity of a lot of of instances that we could customize, and by customizing those, by again dividing things up between standard VT, high VT, and low VT, manage the power dissipation, manage the size of the device, manage the performance of the device in multiple areas. So we've been able to kind of, again, prove a very significant point that you can get a lot of leverage out of optimization and customization of these instances. Incidentally, this is done in TSMC's 28 nanometer HPM process. So with that, I'll close. Again, our number one target for our customers is to minimize risk. Our number two opportunity to help our customers in would be either in being able to give you the optimized chip at the cost that you want, or give you the cost with the most optimized chip that you're looking for. In any one of those conditions, when the 50, 40, 60% of your device is being consumed by the memory, and we have the chance to optimize that, we believe we can give you that optimized chip at the lowest risk. A lot of the cases are that I mentioned here are actual real cases that we've done. We can get into more details if you'd like to speak with me afterwards. But if there are any other questions, I'm happy to answer.
Questions?
Techniques that you use, I'm sorry, what kind of techniques that you use for doing that memory optimization? And do you do it on an individual component by or memory block by memory block basis, or you do it across memory blocks?
It depends on the application. It's a great question. The question is, how do we go about customizing the memories, if you will? Sometimes we can produce a compiler based on the optimization that's required. And that if those instances coming from the same family could take advantage of the same features that wasn't available in a standardized kind of a compiler, that compiler may give us the leverage that we're looking for. And it could be in form of features, it could be in the form of sizes, it could be form of other things that are associated with that, or type of implants that we've used. In other cases, we take instances one at a time, if they're repeated many times in different opportunities or different situations, and we optimize those per our need. And we take it all the way back to the schematic, to the source code, if you will, and optimize it in that sense, or by doing more simplified kind of changes by reducing risks so that we can do qualification by extension. Again, we're looking for the most mitigated risk path. If we can't get it with the most mitigated, then obviously we just kind of turn on the knob, if you will. The question is, do we have our own tools and do we have our own memory compilers? The answer is correct. We use industry standard EDA tools. We have written our own kind of methodology and flows, if you will, to design these memory compilers, and we have our own compilers. We have compilers anywhere from 180 nanometers all the way down to 28, and today we're working on 20 nanometers. Does that answer your question?
Question here.
You said in order to improve timing, you could override the system. However, how to do the trade-off between power and the timing? When the voltage increase, the power consumption may also increase.
So it's a fine balance. You're absolutely right. So what we do is we select certain areas of the device where we can overdrive without the implications and or make trade-offs. And the trade-offs are usually discussed with the customer. Here's what you're going to lose if we're going to gain this. And every system has its own specification. And that's just a matter of negotiation and doing the proper trade-offs. You don't always gain everything that you're looking for from a PPA perspective. But if you're selective about it and you can trade it off, then you're going to be able to get a little closer to your more optimized of a device. But you won't get all three.
Manufacturing synergies, can you elaborate on that a little bit?
Manufacturing synergies.
The SMS...
the different groups, the three different businesses.
For the fabless companies?
Sure. So I talked about a business unit that we kind of put together about 2 years ago called SMS, or Semiconductor Manufacturing Services. It is effectively taking over the operations, all the operational functions of any chip company. So anywhere from test engineering to product engineering to qualification, reliability, logistics, all of that stuff. We have systems in place today that are very automated, and they do the logistics parts of it in a very automated kind of a way. We have a very extensive list of suppliers that we use and have a very strong relationship with. We have insight into a lot of our suppliers' roadmaps. So once we become, if you will, a virtual VP of Ops of our customers, we can sit down and discuss with our customers what the roadmap of the suppliers and how does that match the roadmap of the customer a little bit more broadly. So that's one big advantage that you get. The other one is overheads in smaller fabless companies might be in the teens, 10, 11, 12, 13%. Ours is much smaller because the company is effectively focused on building and designing and shipping chips. So our ability to hire and retain a lot of folks that are very good at their job, especially in the back end side of things because it's our core business, is also probably higher than somebody who might get a chip this year to work on from a test engineering perspective and has to wait and twiddle his thumb for a year until the next chip comes out, just because the frequency is not as often in some of the smaller or medium-sized type semiconductor companies. So those are the efficiencies that we can pass on and also increase quality and productivity for the operations end of the chip.
You don't have your own in-house test facility, but you work with the test facility suppliers to make it happen.
We've looked at the economics of owning your own, and unless we haven't reached that number yet, but unless you're producing millions and millions of chips, you will not see the efficiencies, and or with the variety of the chips that we manufacture and test, the access to the different types of test equipment actually gives us a better efficiency to go out and buy it at bulk, if you will. So if we need a J750, if we need a Flex, if we need a 93K, we, based on the requirements that we've got, it's very much like a central operation organization of a Broadcom, for example, trying to service all the different business units, anything from a 15-cent chip all the way up to a $500 network processor chip. You're going to need all kinds of different things, and by having it, you're not going to get the efficiencies that you need. So yes, we rent it. JW.
Is that correct?
Is that
one of the slides had 328 megabits. Is that the system or the chip?
That's on a chip. So the device is, the device is actually in a network processing kind of an application. It has a huge amount of memory, and the number that I quoted you is an actually exact number. I didn't make it up. It's about without. That's without. Any other questions? Glad I'll be around if I can answer any other questions for you. Thank you very much for your time. I appreciate it.